The Northeast Pacific is defined by a silent structural contradiction. Roughly 100 kilometers off the coast of Vancouver Island, 3 miles beneath the oceanic surface, a slab of solid rock the size of a small country has dropped vertically into the dark. There is no surface expression of this event, no plume of displaced sediment, no hydrothermal venting, no visible fracture line cutting through the water column. To any vessel passing directly overhead, the ocean appears entirely static, yet beneath 3 miles of cold water, the floor of the Pacific Ocean is being torn in half. For decades, regional hazard models for the Pacific Northwest have revolved around a single, well-documented threat, the Cascadia subduction zone. The system is known for producing the magnitude 9 megathrust earthquake, an event that will rupture the boundary from Northern California to British Columbia, driving 4 to 5 minutes of violent shaking and delivering a coastal tsunami within 15 minutes. That hazard remains grounded in deep time mechanics and historical sediment records. However, seismic data published in late 2025 by a team led by geologist Brandon Shuck at Louisiana State University reveals an additional, highly anomalous layer of complexity. The very engine driving this megathrust system is actively coming apart at the seams. Upon publication of these findings, the initial public interpretation leaned toward a comforting assumption. If the subduction engine is shutting down, the overarching earthquake hazard must be collapsing with it. According to the geophysicists who mapped the structure, that conclusion is fundamentally incorrect. To understand why a decaying tectonic system does not equate to a safer coastline, one must examine the physical reality of how a subduction zone terminates. Tectonic plates typically move at velocities comparable to human fingernail growth, a few centimeters per year. When an oceanic plate collides with a continental block, the denser ocean floor is driven downward into the mantle to be thermal processed and recycled. Subduction zones are the primary engines of planetary crustal movement. They construct mountain ranges, feed volcanic arcs, and generate every earthquake above magnitude 9 in recorded history. Yet these mechanical systems cannot operate indefinitely. If subduction continued unimpeded across all margins, oceanic basins would close completely and plate tectonics would freeze. Geology has long recognized the fossilized remains of extinct subduction zones, but scientists had never documented an active system in the process of dying until the marine expedition off Vancouver Island captured it in high-resolution seismic profiles. The physical feature mapped off the coast is a vast, continuous slab tear cutting entirely through the plate's structural envelope, from the upper crust deep into the underlying lithospheric mantle. Along this fracture, one side of the oceanic slab has dropped vertically by approximately 5 kilometers, or 3 miles, relative to the adjacent block. To frame that metric, this vertical drop exceeds the topographic elevation of Mount Everest, measured from base camp to summit. This entire structural displacement is submerged, hidden, and actively propagating. According to the primary researchers, the cross-cutting fault responsible for this displacement is nearly, but not yet entirely, torn through. This critical metric, that the slab is close to complete structural severance, forms the mechanical core of the anomaly. The fundamental question is no longer whether the plate is breaking. The high-resolution seismic data confirms that it is actively fracturing. The systemic question that emerges is what the structural breakdown of a subduction engine does to the stress loading of the megathrust fault itself, and how the physical termination of a plate alters the behavior of the single most dangerous earthquake boundary in North America. Direct imaging of a deep lithospheric fracture buried beneath 3 miles of ocean and miles of solid rock cannot be accomplished through physical drilling or optical cameras. The empirical mapping of this structural breakdown relied on seismic reflection imaging, a geophysical technique that functions as an acoustic ultrasound of the planet. During the 2021 Cascadia seismic imaging experiment, designated Cassie-21, the research vessel Marcus G. Langseth traversed the Northeast Pacific under open funding from the National Science Foundation. The vessel towed a 15-kilometer streamer cable, roughly 9 miles in length, fitted with ultra-sensitive hydrophones. By emitting acoustic energy pulses down through the water and deep into the rock, the team recorded returning echoes, reflected off internal density boundaries, and broken rock strata. Processing millions of sound wave arrival times allowed geophysicists to compile a high-resolution cross-section of the Earth's crust, effectively turning the ocean floor transparent dot. This acoustic mapping targeted one of the most structurally congested tectonic nodes on Earth. While standard hazard models depict a simple two-plate margin off the Pacific Northwest, the northern terminus of the Cascadia subduction zone is a dense four-plate intersection packed into a span of just 300 kilometers, or roughly 186 miles. Squeezed between the overriding North American plate and the massive Pacific plate are two smaller oceanic fragments, the Juan de Fuca plate and the Explorer plate. In this tightly confined area, immense directional forces cannot resolve cleanly, creating the exact conditions required to observe a subduction engine in the act of dying. The resulting seismic data produce two primary visual sets, a planar map of the seafloor and a three-dimensional structural cutaway. The map demonstrates that the fracture is not a clean singular crack, but a broad band of shredded crust known as the Nootka fault zone, measuring 20 kilometers or 12 miles in width. This zone is composed of a braided network of active faults, anchored by the northern and southern Nootka fault strands. Offsets along visible scarps across the seabed confirm that this deformation is currently active, positioned directly at the deformation front where the ocean floor begins its descent beneath Vancouver Island. The three-dimensional cutaway exposes the internal mechanics of the plate. A continuous vertical fracture wall cuts completely through the 4-mile thick oceanic crust and deep into the rigid lithospheric mantle beneath. Along this vertical wall, one side of the plate has dropped by 5 kilometers, or 3 miles, relative to the adjacent block. The Juan de Fuca plate continues to drive downward beneath the continent, while the smaller Explorer plate has stalled, refusing to sink and tearing loose to form an orphan microplate. Researchers compare this process to a train slowly derailing car by car, where the Nootka fault zone acts as a set of natural scissors, slicing the plate into independent fragments and forever altering the regional stress distribution. An examination of seismic activity along the 75-kilometer or 47-mile slab tear exposes a counterintuitive principle of geophysical analysis. Along this line of fracture, certain segments exhibit continuous micro-seismicity, while adjacent sections remain entirely silent. Conventional intuition interprets seismic quiescence as stability or healing. In physical mechanics, the exact opposite is true. An earthquake requires friction. It occurs when locked masses of rock accumulate elastic strain until the frictional threshold is exceeded. Where a fault goes completely silent, it indicates that the rock is no longer locked. The structural connection has been severed entirely. Friction no longer exists to store energy, meaning the silence marks a section of plate that has already finished detaching. This process of piecewise, or episodic termination, demonstrates that subduction systems do not fail instantly. They unravel incrementally as stress redistributes across adjacent blocks. The primary driving mechanism behind this localized death is thermal buoyancy. Ocean crust originates at spreading ridges, where rising magma cools into solid rock. As a spreading ridge approaches a subduction trench, the incoming crust is exceptionally young and hot. Hotter crust is less dense and structurally resistant to subduction into the cooler mantle. When one section of a plate resists sinking, while an adjoining section continues its plunge, immense shear stresses accumulate along transverse faults, forcing the plate to shear apart. This mechanical breakdown highlights a severe misinterpretation regarding temporal scale. The termination of the Cascadia subduction zone operates on deep geological time, advancing at mere millimeters per year across millions of years. In contrast, coastal seismic hazard operates on human timescales, measured in centuries. The physical reality of a dying plate does not alter the immediate stress state of the locked megathrust fault. To evaluate the true baseline of this threat, geophysicists examine the historical record of the last full margin rupture, which occurred on the evening of January 26 in the year 1700. The magnitude 9 event caused immediate coastal subsidence, dropping forests by up to 2 meters and creating the salt-drowned ghost forest still preserved along the Oregon and Washington shorelines today. 10 hours later, the resulting displacement sent a massive tsunami across the Pacific Ocean, striking the coast of Japan, where scribes documented an orphan tsunami arriving without a local precursor earthquake. Turbidite sediment layers indicate 19 to 20 such megathrust quakes over the past 10,000 years, establishing a recurrence interval that places the modern era squarely within the statistical window of re-rupture. The discovery that the subduction plate is tearing does not mitigate this accumulated strain. A dying engine remains fully loaded with stored elastic energy. However, the presence of the slab tear introduces a critical variable into how a future rupture will propagate. When an unzipping fault rupture, traveling at 2 to 3 kilometers per second, reaches the 20-kilometer-wide Nootka fault zone, two distinct mechanical outcomes are possible. The tear may function as a structural firebreak, absorbing acoustic energy and halting the rupture to cap the total magnitude of the event. Alternatively, a high-momentum rupture may leap across the shattered gap, unzipping adjacent segments and compounding the scale of the cataclysm. Resolving whether this deep lithospheric wound acts as a barrier or a conductor remains the central challenge for modern seismic hazard modeling. The fundamental value of mapping this deep lithospheric fracture lies in placing modern geophysical observations into an overarching planetary framework. For decades, geologists recognized that subduction zones must eventually terminate to prevent the total closure of ocean basins and the complete lockup of global plate motion. Yet, researchers lack direct observation of a subduction system actively unraveling. Historical evidence was limited to fossilized remnants, most notably the orphan fragments of the ancient Farallon plate, scattered along the seafloor off Baja California. The Farallon plate once subducted beneath the entire western edge of the North American continent before fracturing and sinking into the mantle. The modern Juan de Fuca and Explorer plates represent the final surviving remnants of that vast ancestral slab. The structural tearing off Vancouver Island is not an isolated event, but the concluding phase of a death process initiated tens of millions of years ago. This mechanical breakdown provides a living template for understanding planetary crustal recycling. As a slab tears and detaches, it generates a subsurface opening, known as a slab window. Through this gap, buoyant high-temperature mantle material upwells into the upper crust, driving distinct patterns of localized volcanism and structural reorganization. The process observed at Cascadia serves as a Rosetta Stone for interpreting similar tectonic transitions documented across the global rock record, from the Mediterranean basin to the western margins of the Pacific. Despite the clarity of these findings, public discourse around the discovery frequently collapses into misinterpretations. Popular narratives tend to conflate geological decay with immediate safety, assuming that a dying subduction machine eliminates the potential for catastrophic failure. This reflects a fundamental confusion between long-term evolutionary trends and short-term mechanical stress accumulation. While the subduction system is undeniably winding down on a multi-million-year timeline, the locked interface off the Pacific Northwest remains fully loaded with centuries of strain. A decaying structural beam under active load can still suffer catastrophic failure long before it completely disintegrates. Further confusion arises when comparing the Cascadia margin to other high-profile fault networks, such as California's San Andreas system. The San Andreas is a transform boundary where plates slide past one another horizontally, producing severe ground motion, but lacking the vertical floor displacement required to generate massive ocean-wide tsunamis. Cascadia, by contrast, combines violent vertical displacement with rapid coastal subsidence and devastating tsunami generation. Evaluating risk along any complex margin requires analyzing how seismic ruptures interact with physical segment boundaries, whether they are lateral strike slip faults, like those near Parkfield, or deep lithospheric slab tears off Vancouver Island. The open, publicly funded research conducted during the CASI-21 experiment demonstrates the utility of systematic observation over speculation. By converting raw acoustic reflection data into precise cross-sectional schematics, geophysicists have replaced vague assumptions with empirical measurements. The slab tear off Vancouver Island does not deliver immediate comfort, nor does it alter the statistical probability of a major event tomorrow. Instead, it exposes the intricate structural realities of a dynamic, evolving planet, proving that even as giant tectonic engines slowly grind to a halt, their final unraveling shapes the immediate hazards of the living world above. The structural deconstruction of the Cascadia subduction zone leads to an unvarnished reality about how humanity perceives natural risk. The discovery of a 3-mile vertical slab drop off Vancouver Island does not deliver an easy narrative. It exposes a profound disconnect between human civilizational timelines and the unrelenting mechanics of deep geological time. Modern society operates on planning horizons of decades, fiscal quarters, or election cycles. The planetary system operating offshore calculates its structural cycles in increments of hundreds of thousands to millions of years. This fundamental difference in scale is where public understanding consistently breaks down. When public commentary attempts to simplify these findings, it usually falls into one of two false extremes. The first is cheap sensationalism, the assumption that a visible 3-mile drop in the ocean floor means an apocalyptic collapse is imminent this week. The second is baseless complacency, the belief that because the tectonic engine is described described as dying, the threat of the big one has been neutralized. Both interpretations fail the test of physical logic. The 5-kilometer vertical drop documented by seismic reflection imaging did not occur overnight. It represents the slow, cumulative offset of crustal stress over vast spans of time. Conversely, the fact that the engine is terminal does not mean its stored potential energy has dissipated. The locked interface between the subducting plate and the North American continent remains tightly bound, accumulating friction and holding centuries of unreleased strain. What the empirical data from the Cascadia 21 expedition actually delivers is a sobering recalibration of engineering and emergency management assumptions. Building codes, coastal evacuation plans, and municipal infrastructure along the Pacific Northwest coast were largely designed around a simplified model of a uniform, continuous fault plane. Integrating a 20-kilometer-wide zone of shredded crust and an active slab tear into these models changes the mathematical calculus of risk. It forces geophysicists and structural engineers to confront complex variables, segment boundary jumps, asymmetrical stress distribution, and localized rupture termination dynamics. The system is demonstrably more complex, fractured, and unpredictable than static models assumed. Ultimately, the active tearing of the ocean floor off Vancouver Island defines the strict physical boundaries of human engineering. We inhabit a dynamic planet governed by thermodynamic limits, gravitational loads, and lithospheric stresses that operate entirely independent of human presence or preference. Science cannot provide a convenient date or time for when the accumulated strain along Cascadia will reach its structural limit and break. What science provides is a clearer, uncompromising schematic of the machine beneath our feet. The dying of a subduction zone is neither a guarantee of immediate catastrophe nor a promise of safety. It is the cold, methodical logic of a planetary system working through its finite lifespan, leaving civilizational infrastructure to adapt to the unyielding realities of a restless Earth.